Welcome to Rise, and this is Physics 101. So in these video lectures, we'll be discussing JEE Mains and advanced type questions. So we'll be discussing JEE Mains and advanced type questions. So today's lecture will be discussing famous leaning ladder problem. Okay, so here is our ladder. Okay, so this wall over here is a frictionless wall. So for that mu equals to 0 and the ground has a frictional coefficient mu. And the question being asked is what is the smallest angle theta the ladder can make with the ground and not slip. So we have to find the minimum value of theta below which the ladder will start to slip. So here the mass of the ladder is equals to m and the length of the ladder is L. So length equals L. Before discussing this problem, we have to draw free body diagram. So we have to draw free body diagram. Okay. So we have to first draw the free body diagram. Here is our wall and here is our ground and here is our ladder. So in this problem what we have to do first is we have to specify all the forces. There is a gravitational force acting downwards, that is equals to mg, and there is a normal force given by the ground that we are calling n1. Okay, there is also a normal force given by the wall that we are calling n2. So there is a normal force by the wall which we are calling n2. Now this ladder will have a tendency to go in this direction. So it will have a tendency to go in this direction. So the frictional force will act on the ladder in the opposite direction. So that we're calling F. So there are four forces in total that are acting on this ladder. So there are four forces. Now before the ladder will start to slip, it will be in a static equilibrium condition. So the ladder will be in a static equilibrium condition. Okay, so for that we have to balance all the forces. So in the equilibrium condition we have to remember to balance all the forces. So this is our first requirement. Not only forces, the second requirement is that we have to balance all the torques. So balance torques. So these are the two requirements for the equilibrium condition. Balance forces, balance torques. So first we'll balance the vertical forces acting on the ladder. So we'll balance the vertical forces. So here in this problem there are two vertical forces, N1 acting upwards and gravitational force mg acting downwards. So they must be equal in magnitude. So N1 equals to mg. So N1 equals to mg. So we have balanced out our vertical forces. Next comes the horizontal forces. So we have to balance all the horizontal forces as well. So horizontal forces. Okay. So in this problem there are two horizontal forces, F and N2. N2 is given by the wall and F is due to static friction. So they must be also equal in magnitude. That means N2 equals F. So we have balanced our horizontal forces as well. So next comes the time for torques. So before discussing torque, we have to find a pivot point. We have to choose a pivot point. Okay. So pivot point is any point about which we are going to calculate our torque. Okay. So you can choose any point in this problem. Okay, you can choose this or this, any point you can choose. But you have to remember one thing about choosing a pivot point, that any stationary point, okay, any stationary point will be fine. So in choosing the pivot point, you have to remember that that point should be or must be a stationary point. So any stationary point will work fine. So in this problem, I am choosing this as my pivot point. So now I will calculate the total torque about this pivot point. There are two forces that will create a torque, N2 and mg. So this is theta. So N2 will create a torque of N2 times the length of the ladder times the sine of theta. So this is the torque created by N2 about the pivot point. Okay. Now this angle here is 90 minus theta. So the torque produced by the gravitational force will be mg times the half length of ladder, that's L by 2, times the cosine of theta. So this is the torque produced by mg. So to balance them out, they must be equal in magnitude. Okay, so these must be equal in magnitude. So I'm writing again n2 times length L sine of theta equals to mg times length L by 2 times cosine of theta. So we have balanced our torques also. So it implies L and L will get cancelled out. That means N2 will be equals to mg divided by mg divided by 2 tan theta. So sin theta by cos theta equals tan theta. So we have found N2. N2 was the normal force given by the wall. Okay, but N2 here is equals to F. That means we have also found F. So it implies F equals to mg divided by 2 tan theta. So we have found also the static friction. But we have to remember one thing about the static friction, that it always comes in equality. So it always comes with inequality sign. So static friction has an inequality sign in it. So that means F is less or equal to nu times n1 normal force. But n1 here equals to mg. That means our static force will be less or equals to nu times mg. So we have found the static friction, that is F is less or equals to mg. So these two equations are equal. That means mg divided by 2 tan theta, mg by 2 tan theta is less or equals to mu times mg. Okay, now mg and mg will get cancelled out. It implies tan of theta is greater or equal to 1 over 2 mu. So for theta minimum, we had to choose an equality sign. So theta minimum equals to tan inverse of 1 over 2 nu. So this is the minimum value of theta below which the ladder will start to slip.